Everyone, we're doing related rates now. I'm going to work through a couple of these problems pretty quickly. We'll see how much time and how much I can get done before we gotta go. Okay, the first question, a hypothetical square is shrinking so that the length of its sides are changing. Okay, so let's draw the hypothetical square real quick. We have a square, so we know all the sides are the same. And the length of the sides, so we have four sides here, right? That's changing at a rate of 4 meters per second. So let's go ahead. I'm gonna call this S for sides. So 1, 2, 3, 4, right? And the rate at which the side is changing, I'm gonna call that ds over dt in relationship to time. That's negative 4 meters per minute. Okay? So you can imagine this is actually shrinking on itself, right? This is all shrinking on itself. And when it's shrinking, it's getting smaller and smaller. And the question is, at what rate is the area of the square changing? So how is the area changing when the sides are 11 meters each? Okay, so we're gonna start shrinking. Once it hits 11 meters, how is the area itself changing? So let's say we want to solve for area. What is the area? How's the area changing? We're given the rate at which the sides are changing. So let's come up with, we're looking for we're looking for dA over dt. That's our goal. So that's what we're going to take the derivative of. Okay. So area for a square is just the equation s squared. And if I take the derivative of s squared and a, it'll be d over dt of a is equal to d over dt of s squared. That's dA over dt is equal to 2s ds over dt. Chain rule. Okay? We did power rule and then chain rule. Well, let's take a look. What do we have here? We're looking for this guy here, right? Looking for this guy. Looking for him. And we have ds over dt. Bam, we got that. We also got our s value here. Okay, that's our s value. And we have our s value. So we have everything we need to solve for it. So dA over dt is equal to 2 times 11. You can write meters if you want, make it look pretty. And ds over dt is negative 4 meters per minute. And when you multiply that out, 22 times negative 4 is negative 88 meters squared per minute. And you can, as you can see, that meter squared is an area, right? Per minute, which is what we wanted. Okay, let's go ahead and move on to the next question. Now this question looks like our first question. It says a hypothetical square is shrinking so that the length of its, in this case, diagonals. So as these problems change, we have to kind of figure out how to do these problems. So I'm going to go ahead and draw this out. So we have again, a hypothetical square. And we know that its diagonal, we can call that's D. So, well, let's not call it D because D would be confusing because DD, right? Maybe we'll call hypotenuse. H is changing at a rate of negative 4 meters per minute. So very similar to our last question. So dH over dt for hypotenuse, right, is equal to negative 4 meters per minute. At what rate is the area of a square shrinking when the diagonals are 13 meters each? Okay, we know the sides, the sides are 13 meters. And we're looking for dA over dt because we're looking how fast the area is going to change. Now, if you remember, since this is a square, I'm looking for s here. How can I get from h to s, right? How can we get from the hypotenuse to the s? Since this is a 45, 45, 90 right triangle, we know the relationship. It's the s and the hypotenuse are related by square root of 2. Going forward, so going backwards from the hypotenuse back to the side, we're going to say it's divided by square root of 2. So s is equal to h over square root of 2. Okay, so we know what the sides are, whatever h is over square root of 2. And we're going to go ahead and take the derivative with, well, let's write our area equation. Area is equal to s squared, in which this case each of those s's is h over square root of 2. So we can rewrite this as h over square root of 2 squared. If you remember that we were given that dh, not s, is what we're given. So we have to change that to our h here. So when we take the derivative of h, we end up with dh dt. And we can multiply that out to make it a little easier. So a is equal to h squared over 2. Or I'm going to rewrite this as 1 over 2. Make it a little prettier. Okay, let's go ahead and take the derivative because we need to find our dA dt, right? We need to get our dA dt. So when we take the derivative of a, that's just dA dt, and we take the derivative of 1/2 h squared, the 2 comes down, that becomes a 2 over 2 is 1, we're left with just h, and h dh over dt. Alright. Oops. I made a mistake here. I didn't call this right. We said this was the diagonals, right? So let's change this to the letter H. I don't want to do the whole video again. Alright. So we know what H is. We know what dHdt is. So dA over d over dt is equal to h, which is 13, times negative 4, meters, over 4 meters, times negative 4 meters over minutes, which multiplies to become negative 52 meters squared per minute. Alright. So sometimes, like in our first problem, everything's kind of set up for you already. And sometimes we have to change things around to fit our situation. In this case, if I had area as s squared, we had to rewrite that. If you didn't know, the area of a square with its hypotenuse is really just your hypotenuse squared over 2. Well, now you do. Or you could just make it up. Okay, that's the next question. Water is evaporating slowly in a circular shaped puddle. Here's my circular shaped puddle. We use blue here. See? Ooh. Come on, blue. Yep. Ooh, that's my subtle. Oh, let's do more circular shape. Circular puddle. And it's evaporating. Okay. The radius of the puddle is slowly decreasing at a rate of 3 inches per hour. So I'm going to say the radius, the rate of the radius over dt is equal to 3 inches per hour. And I'm going to put that as a negative because we're actually going in. The radius is decreasing. So here's my radius, r. And as the puddle starts to evaporate, the circle gets smaller and smaller and smaller. Assuming that the puddle retains a circular shape, at what rate is the area of the puddle changing when the radius is 2? Okay, so they told us our radius is 2, and that's not constant, right? Because we're shrinking from that value, and we're looking at the area of the puddle. So we're looking for dA over dt. So the area of this circular puddle is pi r squared. And so just a hint, when we have stuff like the derivative, how am I going to use dr dt? Well, I need to take the derivative of r. How am I going to find dA dt? Well, I have to take the derivative of a, and this is just kind of a hint of what to do. So let's go ahead and take the derivative of the area to see our change. So dA over dt is equal to pi is a constant, so pi, and we're left with 2r dr over dt. And as you can tell, r2, oops, I need a different color pencil. R2, oh, come on, R2, and our dr dt, we have everything we need. So dA over dt is equal to pi 2 times 2 times negative 3, this is inches, inches per hour. And 2 times 2 times 3 is 12, so negative 12 pi inches per hour. Inches squared, I'm sorry. All right. So now that we're done with the easier questions, the basic idea of related rates, let's go to some harder questions. These are different shapes we're going to look at. First is a conical paper cup. So that's just a cone. Right? And we've had these paper cups before. And it tells us it's 20 centimeters tall with a radius of 10 centimeters. So here is the height, which is 20, and the radius is 10 centimeters. The bottom of the cup is punctured so that the water level is going down at a rate of 3 centimeters per second. So the height here, I'm going to call this h, and this is r. dH over dt is equal to negative 3 centimeters per second. At what rate is the volume of water in the cup changing when the water level is 7 centimeters? When the height is 7 centimeters, what is the rate of volume? What is the volume of water changing? So dV over dt. Okay, let's go ahead and stop a problem for this. We're trying to find dV dt. We need h. See how we have h here? Okay, so let's just look at what does the volume equation of a cone look like. V is equal to 1 over 3 pi r squared h. So you need to know these volumes for these different shapes, so we don't waste time, especially on the AP exam, or at least how to use them. Sometimes they'll give us different sets of figures. Okay. Now the hint is that I don't want to deal with all 3 variables. We could, but as you can see in the problem, there's nothing to do with r here except our original r. So we're going to go ahead and use a trick about switching r's for h's. And here is the trick. If you look over here at this triangle here, this triangle here, see that? As the triangle shrinks, it will follow the same ratio. So the trick for these problems is that you create an equation with r and h and the radius and the height that they give us already. So these will always be related. It's the same ratio. If you tilt this graph over and draw it this way, some of you guys have seen triangles that look like this. Right? And as the water's shrinking, so is the overall values. And they're all related in how they're shrinking. Okay? And those two. Okay, so let's go ahead and write that formula. So we're saying r as to h as 10 is to 20. Or as we saw for r is equal to h over 2, because the 10 and 20 divide out to be 1/2. So the point here is every time you see r, we're going to just substitute it for h now. h over 2. So we rewrite the equation. V is equal to 1 over 3 pi times h over 2 squared h. So a little too high, h. And that leads us to 1 over 2 times 2 is 4. 4 times 3 is 12. H cubed pi. That's our volume. Now we are asked to take the derivative from over here. Okay, let's go take the derivative because that's we want dv dt. So dv over dt is equal to the constant 1 over 12. And then we can say pi if you want. And then the derivative of h cubed is 3h squared dh over dt. And as you can see, we have our h value before. See, h right here, h. And we have dh dt. Huh? We have everything we need. So this is equal to pi, let's say 3 pi over 12 is over 4. Then we have h squared, which is 7 squared, times negative 3 over, sorry, not 3 over, this was centimeters, and negative 3 centimeters per second, which gives us the answer. Okay, so we're going to multiply those together. 49 times 3 is 147. So negative 147 over 4 centimeters cubed per second. And as you can see, centimeters cubed is the volume over time. Right. Oh, sure, I forgot to write pi. Pi. Yep. Okay. Okay, a spherical snowball melts so that its radius decreases at a rate of 2 inches per second. At what rate is the volume of the snowball changing when the radius is 4 inches? All right, the same idea. The volume of a snowball, or volume of a sphere, is equal to 4 over 3 pi r cubed. Right, so we have a snowball, and of course it's going to be melting, right? Melting. And the radius is decreasing. The rate of the radius is decreasing at a rate of negative 2 inches per second. At what rate is the volume of the snowball changing when the radius is 4 inches? So how is the volume changing when the radius is 4 inches? Okay. So in this problem, as you can tell, we're trying to find dv dt. Well, how to get dv dt? We take the derivative of this over here. And we're given dr dt, and we can use that. When we take the derivative of r, that will give us dr dt. So let's go ahead and take it. Oops. So dv over dt, the derivative, is equal to 4 over 3 pi 3r squared dr over dt. And of course, like I mentioned before, we know what r is. Okay, we know what dr dt is. So let's go plug that in. dv over dt is equal to, these 3's divide out. These 3's divide out, right? These 3's divide out. We're left with 4 pi. R is 4 inches. Dr dt is negative 2 inches per second. And that becomes, okay, as we multiply all these together, 4 times 4 is 16. 16 times 4 is 64. And 64 times 2 is 128. So negative 128 pi inches cubed per second. Okay, let's do one last problem. A hypothetical cube shrinks so that the length of its sides are decreasing at a rate of 3 meters per minute. At what rate is the volume of the cube changing when the sides are 5 meters each? So our cube, draw a cube. suppose okay. Q means they're all the same side, so there's S, S, and S going up. So the length of the sides are decreasing. So ds over dt, the sides are decreasing at a rate of 3 meters per minute. What is the volume? How's the volume changing? So dv over dt is equal to what? When s is equal to when the sides are 5 meters. Okay. So we take the derivative of our volume equation, and this is a simple cube. So the volume of a cube is s cubed. And if you take a look here, some hints are, hey, if I take the derivative of s is ds dt, and if I take the derivative of v is dv dt, and we can plug in s. So we pretty much have everything we need. dv over dt is equal to 3s squared ds over dt. We're just going to plug in our... Okay, we can now plug in our final values for s. We have s here, we have ds dt. So this is equal to 5 meters squared times negative 3 meters per minute. Multiply that together, it's 5 times 5 is 25. 25 times 9 is 225 negative meters cubed per minute. So related rates can be pretty easy sometimes, and of course the questions can get more harder than this, but the basics are here, where you create an equation and we see what we're given and see what they want us to solve for, and then we end up taking a derivative and then plugging in our knowns. And that's a good start, I think. If you have any questions, go ahead and email me, and I'll get back to you from there.